Assalamu alaikum. Well, so let me show you what this circuit actually do. So after running the simulation, you can see that if I click on the output, we obtained a square wave, and the square wave is pulsating from positive 15 volt to negative 15 volt. Well, so how this circuit actually works, let's see. Actually, this circuit is called astable multivibrator circuit. And why this is called astable multivibrator, you can understand it later. Well, so let's say that this is the output voltage V out, and let's draw a waveform here. Let's say when you switch on this circuit, at initially V out is equal to, let's say, positive 15 volt. That means the V out is positive. Let's say, just assume that. So V out, so you can see that V out is 15 volt. So after applying a voltage divider here, you will get this voltage is 7.5 volt, the half of this 15 volt, right? And you will see that this voltage appears here. That means this point's voltage is 7.5 volt. Okay, now you see we have a capacitor here and a resistor here, right? And as this voltage is 15 volt, now capacitor will be charged in this path. Capacitor will be charged in this path through this resistor. Well, so that means capacitor will be charged, and this capacitor's voltage will be 1 volt, then after some time 2 volt, 3 volt, and gradually it will become 7 volt, 7.5 volt, and then when this voltage will become slightly greater than 7.5, let's say 7.001, you see this voltage appears here. And now this inverting terminal's voltage, or this minus terminal voltage, is greater than 7.5, and as this is now greater than 7.5, you will see that this output voltage will be no longer positive, rather it will be now negative 15 volt. That means after using a voltage divider, you will see now this point's voltage will be minus 7.5 volt, and also this point's voltage will be minus 7.5 volt. Okay, so now as capacitor's charge is 7.5 or around 7.5 volt. Okay, let me draw this circuit again. So as now output voltage has gone to minus 15 volt. Okay, now let's see what will happen in this position. You see capacitor's voltage is 7.5, but this point's voltage is minus 15. That means now capacitor will discharge in this path. Now capacitor will discharge in this path, and as it is discharging, the voltage will be reduced. That means after some time you will see its voltage is 6, then 5, then 4, 0, minus 1, minus 2, minus 3, and by this way it will gradually become minus 7.5 volt. And after this moment, when this voltage is slightly less than minus 7.5, let's say minus 7.50001, you see now this voltage is less than minus 7.5 volt. You see now this voltage appears here, and this voltage is less than the positive terminal or non-inverting terminal voltage. That means now the output voltage will be no longer minus, now it will be positive 15 volt. That means this graph, you see this graph here, this graph will again goes to positive 15 volt. And you understand that we have two states here, one is high and another is low, and both the states are not stable, because sometime it is high but it is not forever high, it again becomes low, and it is also not low forever, it again becomes high. And that's why this circuit is called astable multivibrator circuit, because both the states are not stable. Okay, so now let's see how to calculate the time period of this circuit. Well, so let me show you. In this position, let's say the output voltage is VCC, the output voltage is VCC, then after applying a voltage divider here, this point's voltage will be VCC by 2 and this point's voltage will also be VCC divided by 2. And you see at this moment the capacitor's voltage is around minus VCC by 2. Let me decrease the size. Okay, so now we know the formula for the capacitor's voltage. So capacitor's voltage, that is V is actually V infinity plus V naught minus V infinity e to the power minus t by RC. Well, so let me tell you what this formula actually telling you. So what is V naught? V naught is the voltage initially. So now if we start the time from this moment, let's say you are starting the time from this moment, so now the voltage is VCC by 2. So let's write here V naught is VCC divided by 2. And let's say after infinite time, what will be the capacitor's voltage? As this voltage is VCC, if you allow this capacitor to, if you allow this point to be, okay, let me tell you here, let's say this point is VCC, forget this opAmp, and here you have resistor and here you have capacitor. So after infinite time, what will be the voltage across this capacitor? The voltage across this capacitor will be VCC. Forget about the opAmp, just focus on this circuit. So after infinite time or V infinity, this capacitor's voltage will be VCC. So let's write here VCC. Okay, similarly this thing is also VCC. Okay, and now when the transition will occur, the transition will occur when this capacitor's voltage is not charging, right? You see this voltage is minus VCC by 2, but output voltage is VCC. That means capacitor will be charged, and now capacitor's voltage will be minus 3, minus 2, minus 1, 0, 1, 2. And when this capacitor's voltage will be VCC by 2, you will see that this voltage appears here and the transition will occur. That means when capacitor's voltage V is equal to VCC by 2, that means in this formula, when the capacitor's voltage V is equal to VCC divided by 2, you will see a transition. I think you understand it. Okay, so let's find the T. Let's say it is actually T1. Okay, so VCC by 2, VCC 3 by 2 VCC e to the power minus T1 divided by RC. So BCC cancels out, then minus half is equal to minus 3 by 2 T1 divided by RC, and we will get ln 1 by 3 minus RC T1. Okay, that means T1 is equal to ln 3 RC. Well, so what is this T1? Actually this is the time when the output voltage remains in positive voltage, that means 15 volt. When the output voltage, the duration for which the output voltage is 15 volt, this is the time T1. Then the formula for T1 is this. But another T1, for another T1, it will remains in the negative voltage. That means if I want to calculate the time period, this is actually 2 into T1, that means 2 RC ln 3. So this is the formula for the time period of their square wave. Okay, so let's see that thing actually happens or not. So what is my R? R is 50k and C is 1 microfarad. Okay, let's see. That means my R is 50k and C is 1 microfarad. So T is equal to 2 into 50k 1 micro ln 3. Well, so let's see what is this. 2 ln 3. So I'm calculating this thing. 1 micro ln 3. So T is 1.0986 second. Sorry. 0.10986 second. That means 109.86 millisecond. Well, so now let's check it in the simulation. So this is my circuit. Okay, so now let's take from here to here, and you see, okay, let me okay, from this point to this point, and you see at the bottom this is 106.7 millisecond. You see at the bottom here, you will see at the bottom here, let me do this thing again. This is 106.64 milliseconds, slightly different than our answer. Our answer was 109, but this is actually 106 or 107 millisecond, and this is because, you know why that is happening. It's because let me show you. It's because okay, you see the voltage is not actually 15 volt, it's actually 14.06. and then if I again go to the here, you see this voltage is not actually 15 volt, it is actually minus 14.06. so that might be the reason. Oh, sorry, that's not the reason. Sorry, that's not actually the reason. Sorry, actually I don't know what is the reason, but that's not actually the reason. If you know the reason, please tell me in the comments. Okay, I actually don't know what is the reason. Maybe this is the reason because the opAmp is not ideal. Maybe that will be one of the reasons, but if you know the reason, please tell me in the comment section. Okay, so but maybe I can tell you the reason, but I'm not sure actually about that. I have had a small resistor here to measure the current, and you see this current is flowing, but ideally we assume that this opAmp is ideal. That means no current should flow in this direction, but you see some microampere current is flowing here, and that means this current may have some effect. This current may have some effect here. I think this current may have some effect here. This capacitor's voltage maybe is charged from in this direction, and also this is charged from in this direction, and both the currents are added here, and that's why this capacitor is charging slightly faster than the calculated value. I mean, we obtained here 109.86, but at the simulation we obtained 106 millisecond. So 3 millisecond 107 millisecond, that means 3 millisecond faster. And why this is faster, maybe, I'm not sure. If you know another reason, please tell me in the comment. Maybe that capacitor is charged from this direction and also from this direction. These two currents are contributing to charge up this capacitor, maybe. Okay, so thank you.